In this video, we're going to start to talk about some examples. So what I want to do is I want to start with, let's start with an example where A is a 2 by 2 matrix that's 2, 5, 1, negative 2. And I want to find all the eigenvalues and corresponding eigenvectors. And corresponding eigenvectors of A. And so what we're going to do is we're going to look at A minus lambda I. Here, A is a 2 by 2 matrix, so the identity that we're looking at is the identity I sub 2. And this is going to be A, which is 2, 5, 1, negative 2, minus lambda times I, which is 1, 0, 0, 1. If we were to multiply lambda through and then subtract these matrices, we'd end up with 2 minus lambda, 5 minus 0, 1 minus 0, and negative 2 minus lambda. So that's A minus lambda times I. So that tells us that the determinant of A minus lambda I is going to be equal to, we're going to have 2 minus lambda times negative 2 minus lambda minus 1 times 5, and that would be 5. And so it turns out that this is going to be, if we square this, we're going to end up with, let's see, what do we get? We end up with negative 4 plus 2 lambda minus 2 lambda plus lambda squared minus 5. And so this whole thing works out to lambda squared minus 9. That's going to be our characteristic polynomial. And therefore, if we solve where the determinant of A minus lambda I is equal to 0, that's the same as solving lambda squared minus 9 is equal to 0. And that happens when lambda is plus or minus 3. So here we're going to have two different eigenvalues. And we know that we can have at most two eigenvalues because the characteristic equation, the characteristic polynomial, is a polynomial of degree 2. So we can have at most two solutions. All right. And so what we can do then is we can look at the eigenvectors. So if lambda is equal to 3, what's going to happen is, so if lambda is equal to 3, I want to find x so that ax is equal to 3x. So here I want to solve ax equals 3x. And another way to think about this is you can just jump right to a minus 3 times I, x being 0. And I think that that's helpful because a minus 3I is going to be what we get when we take a minus lambda I and plug in lambda equals 3. And so remember what we're trying to do here is we want to solve a minus 3I times x equals 0. A minus 3I is, let's see, if lambda is 3, we're going to get negative 1, 5, 1. And again, if lambda is 3, we get negative 2 minus 3 is negative 5. And indeed, this is going to be a matrix that has determinant 0 because one row is a multiple of the other. And let's say x is x1, x2. So we're thinking of x as a vector, if we want to think of it that way, with components x1 and x2. And we want this to be equal to the 0 vector. And so we can do everything that we know here. And if you were to think about this as a matrix, what this really leads to is this leads us to solving this augmented matrix, negative 1, 5, 1, negative 5, augmented with 0, 0, right? We introduced matrices at the beginning of the semester to help us facilitate the process of solving these systems of linear equations. So what we're going to do, and the reason why we've talked about parameterizing, really everything that we've done so far is going to lead up to this computation of eigenvalues and eigenvectors, and what we'll eventually talk about with diagonalization. So what we're going to do is let's try and solve this system, and it turns out that if we solve it, I'm going to leave the details to you, but it turns out that if we solve the system, what we're going to end up with is 1, negative 5, 0, 0. So that's going to be our system. And if we wanted to write all of the solutions, what we could do is we could parameterize this by letting, say, x2 be t, and then x1 would be 5t. So our eigenspace, we might as well write it like this, our eigenspace corresponding to lambda equals 3, remember this is the set of x values where a minus 3I times x is equal to 0. Here we're thinking of x as a vector. So just if that helps us remember that we're talking about x as a vector. What we're really doing, by the way, this E3 is nothing more than the null space of a minus 3I. So I think it's helpful just to think about this in terms of the null space of a matrix, which we've already talked about. And it turns out that this is going to be the span. This is going to be, well, this is going to be equal to the set of vectors x1, x2, so 5t, comma t, where t is allowed to be any real number. In other words, this is going to be the span of the vector 5, 1. That's going to be the eigenspace corresponding to lambda equals 3. And that's it for this eigenvalue, right? We found this, for this eigenvalue, lambda equals 3. We found an eigenvector, which is 5, 1. And a little more than I asked for, we found the eigenspace, E3. Let's do the same for lambda equals negative 3. So if lambda is equal to negative 3, what we want to do is we want to look at, we want to solve a minus lambda I times x equals 0. In other words, this is going to be the same idea. We're going to look at a minus lambda I. Where are we here? A minus lambda I when lambda is equal to negative 3. So we're going to end up with 5, 5, 1, 1. And then we have to solve when that's equal to 0. So we're going to augment that with a 0 vector, solve it using all the wonderful properties that we know about matrices. It turns out that the solution is going to be 1, 1, 0, 0, 0. And then, again, let's let x be the vector x1, x2. And let's let x2 be t. x1 is then negative t. And so e negative 3 is going to turn out to be, you remember this is the set of all the vectors x where a minus negative 3I times x is equal to 0. And that's going to be, it turns out, all of the vectors of the form negative t, comma t, where t is in R. So this is going to be the span of the vector negative 1, 1. And again, I just want to emphasize, eigenvectors are not unique. It turns out that this is also the span of the vector 1, negative 1. Any multiple of that vector will do.